There, right. Thank you so much. Right. Uh yeah, so this should be a very short topic today. We'll try and focus on moments with today, and then we have center of gravity to maybe Wednesday. Maybe Wednesday we try and complete center of gravity. All right. Um, Depending on how far we reach today, we can just like not have class on Wednesday, and I just give you the activity that you're supposed to do. All right. So we're going to define the moment of a force. All right. We're going to define the moment of a force and apply the principle of moments, explain the actions of common tools and devices as levers and devices such as levers, determine the location of the center of gravity of a body. Maybe we can do this on Wednesday. Relate the stability of an object to the position of its center of gravity and its weight. All right, that's what we want to accomplish. This is straight from your syllabus as always, right? And the notes will be provided on Google Classroom as always. Right. All right, so forces and moments, right? So what is a moment? A moment is that force that happens, right? Let me see something here. Right, so it's a moment is caused by a force which occurs, right? And it causes the object to move in a rotational direction, right? So it's a turning effect of a force. That's what we call moments in physics, right? Like Miss Van Horn is having trouble joining. Right, so is that turning force? Is the effect of the turning if is the effect of the turning of a force, right? So the force to the act in this particular direction. So let's say that the force act in this direction vertically downwards, and then you'll find that because the force is moving downwards, there's a turning effect of the spanner, right? So spanners are used for tightening and loosening screws. They help to produce a larger turning effect. These are very important tools because we cannot we can't turn it off ourselves. Like we can't use our fingers to turn this. It will be very, very difficult, right? So we use spanner, right? We use the spanners and it helps a lot. So the longer the spanner, the greater the turning effect of a force, right? Once we have a longer spanner, once we have once one or if you realize you have different sizes of spanners, right? If the spanner was at this particular length instead of this, right? You'll find that you have to apply a larger amount of force in order to get it to turn, right? We all agree? We're all okay so far?
Yes, sir.
All right. Okay. Yes, very good. Wonderful.
Yes, sir.
All right. Uh, so we want to look at the formula for calculating the moment of a force, right? The moment of a force is simply the force times the perpendicular distance, right? This is very important that it's perpendicular, right? The distance from here to this particular force here. That's our moment. So it's the product of those two. The product of those two factors, our distance here and our the distance away from the center to our force. And this should of course be perpendicular at 90 degrees. right? Very easy. Now, what is the unit for force again?
Newtons.
Newton.
Newtons, right? And what is our unit for distance?
Kilometers, no?
Meters.
Yeah, so meters, right? That's what we usually use,
Yes, sir.
right? And moments may be described as clockwise or anti-clockwise, right? So if which side is this? Clockwise or anti-clockwise,
Clockwise.
right? And of course, so let me just put it here, clockwise. And this, of course, would be anti-clockwise. So we have two different classifications of moments, right? And these play a very important role as we move forward, right? I'm going to stop for a second. I'm going to see if I can bring up the activity. If it's not coming up, then we'll just continue. All right, but I want to show you something before we go any further. So we're going to move now to the principle of moments, which talks about the balancing of a system. Right? Talks about the balancing of a system. Like for example, a seesaw. Right? I'm sure we're all familiar with a seesaw, right? All right, Lex is coming up. Let's see this one. All right. So let me know if you're seeing this.
Yes, sir.
Yes, sir.
So without these under it, right, we see that the system is balanced, and that's what we should ensure first. If we're doing a lab and by regards to center of gravity, we have to ensure that the ruler is balanced, or whatever system we're going to use. We have to ensure that it's balanced first. Now, let's place this back under, so this distance doesn't change. And if we add a 15 kilogram over here, right? Let me get my ruler. 15 kilogram at, all right, that's going to be a large first, at 1 meters away from the center. 1 meter away from the center. And we add a 10 kilogram here, right? Let's put it the same at 1 meters. Is that system going to be balanced?
No, sir.
No,
Right.
sir.
What we have to do with this, put it in or out, as you just spoke about.
In, sir.
No,
Out.
yeah, because if further we move it away, it's going to have a larger turning effect, right? So a system is going to balance. Now, if we place it out further, we see that it is beginning to get balanced. So they're not the same. They're not the same
Wait.
mass, yeah, or the same weight. Thank you. But neither are they the same distance away from each other, right? But because of the moment or the turning effect, this is moving in the anti-clockwise direction, and this is moving in the clockwise direction. The 10 kilogram is moving in the clockwise direction, right? These two will balance out, and we'll just look at that right now. So we should ensure, sorry, let me just say this before I close this off. We should ensure that the moment on this side is equal to the moment on this side. That's when they're going to actually balance out the entire system. When the moment on this side is equal to the moment on this side. No, let's calculate the moment for this side. What's it say is moment again?
Force times this perpendicular distance.
Right. So what is our force here? So 15. Right? No, not really. That is our mass. Times what? Breaking up. Miss Johnson?
Yes, sir.
Yeah, you said 15 times what?
Times a meter, sir.
All right, not entirely. Not entirely. Do we all remember weight? Remember we spoke about weight in the past? Yes, no, maybe so. You all remember weight? So weight is a force that we apply to the earth because of gravity. You remember that? So weight is different from force. It's different from mass, right? So we have a mass, which is the same for every, let's say on every planet. Let's say the mass is the same on every planet, but our weight is different because of the different forces of gravity, right? So the force of gravity is, right, what is the acceleration due to gravity again?
9.8.
Right. And let's just round it up to 10, right? Is that okay? So G is 10 for this particular exercise. No, the weight is force equal mass times what?
Acceleration.
Yeah, so this looks familiar now, right?
Yes.
Right, so this is our weight, right? Our weight is mass times gravity. If you want to calculate the weight of an object or the force that an object applies on a particular on the earth, right? Or if a mass is pulling down, let's say this system here that we had before, right? Then we'd use mass times gravity. So what is our weight for this now?
15 to 1500.
Yeah, no, 1500.
1500. Because you use
No, 15 times, 15 times what?
10.
Yeah,
That's
so
it.
that would be 150, right?
Oh,
Yeah,
yeah.
that would be 150. And our mass over here, right? What is our weight for the mass over here?
100.
100, right? 100. And then if we times 15 times 1, if we times 150 times 1, how much do we get?
150.
Yeah, 150. And if we times 100 times 1.5, how much do we get?
1,500.
No.
150.
Yeah,
Yeah.
yeah, 150. So realize that it's 150 over this side and 150 also over this side. Is anyone not clear? Please say something, send it in the chat, right? I don't want at the end of the class somebody says, sir, I don't understand what you're saying, class. Right?
Sir, what me want to know is, sir, or I get it 10 again, times both side.
So again?
Or I get it 10 for times it on both side.
10? Right. So remember we just spoke about the acceleration due to gravity, right? This guy right here. So its mass is the mass of the object. For example, the mass of the object was 10, and then the gravity is also 10, right? So this is our mass, and then times 10 as well. So the gravity is also 10, and this would give us 100, right? 100 newtons. So that's a force or weight. Force or weight, right? Force or weight. Are we all clear now? Please let me know.
Sir, may I listen still?
Okay. All right, so I'll take that as a yes. We're all clear. So moments, as we said, can be described as clockwise or anti-clockwise, and a moment of force is also called torque. So if you see a question coming up in CSEC and you see torque, don't say Mr. Treasurer did not teach you that, or Mr. Treasurer did not tell you that. I made it clear down here. All right, now we can move on, right? As we said, we introduced it, but now we look on the actual application and the principle of moments. Now, what is our moment here? We have 5 newtons away, 4 meters away from the second, right? How do we calculate the moment? 5 times 4, right?
Yes, sir.
Yeah, 5 times 4. And that would give us 20. And you want to state that it is 20 clockwise, of course. And we have our another system up here, and it has a force of 3 newtons, and it's 5 meters away. And how do we go about calculating that?
5 times 2.
Right, so we see that this topic is very easy, right? A very easy topic. All right, so we'll go now to the principle. No, okay, we're going to do this calculation now before we go to the principle of movements. Let's just do this quickly. So we have a 4 newtons and it's 0.25 meters away from the center, right? So the moment will be equal to force times distance. So what do we have here for force?
4.
Yeah, 4 times
Times
0.
0.25.
Yeah, and what do we get?
1, sir.
Right, so we get 1 newton, right?
Yes, sir.
No, 1 newton
Clockwise.
meter. Sorry, 1 newton meter. And that's our unit. Remember?
Anti.
Newton meters.
Sir, can go over that again, please?
This particular section.
Yes, sir. About the newtons. The question that we just did about the 0.25.
Okay. So we have our force here, 4 meters, acting in this direction. So this will be anti-clockwise. Right? And this is 0.25 meters away from the center, or our fulcrum right here. 0.25 meters away. So our moment is force. To calculate our moment, it is force times distance. That's how we calculate our moment. Our force is 4 newtons, right?
Yes, sir.
Yeah, and our distance is 0.25. So it will be 4 times 0.25, and of course we get 1 Newton meters. Are we clear now, Mrs. Tomlinson?
A little bit.
All right, don't worry. We can do one more. Right over here, Ms. Tomlinson, you can do this one. All right, what is our formula again?
Sir, force times the distance.
Force times distance, and we have 5 newtons here, right? As our distance or force.
As the force.
Right. Yeah. So force times what exactly?
0.50.
0.50. right? So we now go ahead and calculate that, and how much do we get?
2.5.
2.5.
New answer.
2.5 Newton
2.5 newtons.
2.5.
Yes, sir.
Yes,
Newton.
sir.
Newtons.
That's not what I'm getting. Oh yes, you're correct. You're correct. Sorry about that. So 2.5 Newton meters.
Clockwise.
Yeah, so thank you so much. We should say anti-clockwise here. And we should say clockwise here. All right, so based on how we're moving, I think everybody's understanding. Is anyone not understanding? Please stop me. Right? Please stop me. All right. Okay, I think that is a yes. All right, so find the total moment acting on the bar below. When more than one force acts in the same direction, their overall turning effect is just the sum of their moments, right? That's what we want to accomplish for this particular slide. So we look on this particular moment here first, right? So the first moment, T1 equal, T1 is a symbol for moments, right?
It's making it so
So
public.
T1 is force times distance, right? And what is our force for T1? This one, the red one? 5,
Newton.
right? And then our distance would be what?
0.5.
0.5 times 0.50. And this would be equal to, we just did this just did something similar to this, right? 2.5 Newton meters, right? And then T2. So it'd be, what is our force?
2 newtons.
2 times
0.20.
0.20.
Why
And
did you put me up first?
that should give us what exactly?
So fake.
0.4.
I'm sorry.
0.4, right? Newton meters.
Obviously I did.
And this is all clockwise.
How dumb do you think I am?
Miss Surgeon, thank you. All right, so we now move to the principle of moments, right? When forces act in a direction, yet still balance, the total turning effect in each direction will be the same, right? So we just did that in the first activity. We saw that if we had, right? So if we had one force over here, we have our system and our Planck, and we added, remember we added that 15 kilogram over here, and then we had, no, that was the case, no, yeah, 15 kilogram over here at 1 meters, right? And then
Right.
we had our 10 kilogram. Question? Okay, 1.5, and this was 10 kilograms. Should be shorter. It should be shorter. 1 second. Right. So 10 right here. And we saw that because we placed the 10 kilogram much further away, right, at 0.5 meters away from the center, right, we saw that the entire system was balanced, and we proved that the moment clockwise was 150 Newton meters, and moment anti-clockwise was still 150 Newton meters, right? So our system was therefore balanced, right? That's the essence of principle of moments. Let's go to the actual formal definition that describes it. So if an object is in equilibrium, right? If you're asked to state the principle of moments, you would state something like, if an object is in equilibrium, the sum of the clockwise moments about any point is equal to the sum of the anti-clockwise moment about that same point, right? And I think, yeah, we can end class on this particular note. So we're all understanding this, right? If the object is in equilibrium as this guy right here, right? The object is in equilibrium. The sum of the clockwise moment, which will be acting on this guy, and the anti-clockwise moment here, they will both be equal. That's what we're trying to accomplish for this class, right? Yeah, so are we good?
Yes, sir.
Yes, sir.
All right, so
Yes.
on this last thing right here, we have a problem, right? Somebody hit a nail in the wall, and we want to try and get it out, right? Because we want to fix up the place and paint the wall, but somebody took a nail and they hit it in the wall. We're trying to get it out, right? Now, if this looks familiar, because if we apply a force here in this direction, force here, there will be a turning effect, right? Because of this. And this is called our fulcrum, right? So about this point, right, if we apply a force, we'll find that it will begin to move in the anti-clockwise direction. It will begin to move in the anti-clockwise direction. Our load, right, would then be affected. It is currently the load, right? I don't want to go, I don't want to try and confuse anybody, but just think about it. If we're trying to pull it and we're trying to pull this, right? It means that our system is sort of balanced, right? It means that our system is balanced. And when the point at which the force that we apply at that point, if the force has to be greater so that it applies a larger amount of moment to that particular load. It has to apply a larger. So this moment has to be greater than this moment here, which is acting in this direction, right? It has to be greater than that moment so that we can pull out that load. That's just what we want to get for that particular side. Not too difficult, right? So we have a little decision to make. We can do center of gravity now, and then you, for next class, you just get your activity, or we can if you want to, you can get the rest of the time, the rest of the 20 minutes, right? Because we'll end this call now in 3 minutes. So what exactly would you want? You want to go to, or you want to wait until Wednesday?
Sir, just go through it.
Let's
Sir,
go
let's
through it.
go through it now, sir.
All right, I only hear 2 persons and 1 more confirmation. right?
Go through, sir.
All right.
What through, sir?
Okay.
Go through.
So, sir, are you going to send the activity on forces, sir? No.
Yeah, I would send it next class.
Okay.
Yeah, at the beginning of
No,
next
no
class.
problem.
Yeah. All right. So I'll end this call here, and then we come back. All right. I'll end this call here, and then we come back. I see Miss Virgo raised her hand. Miss Virgo. Okay. That seems like a mistake. All right. So I'll end, and then we'll come back. All right. Join. Use the same link to join.